Have you ever really stopped to think about it? That invisible energy that connects your phone to a cell tower, heats up your food in just a few seconds, and travels 93 million miles through empty space from the sun just to warm your face? Well, today we're going to pull back the curtain and make the invisible visible.
Okay, let's just jump right in with a little riddle. What in the world do your microwave, the sun, and your Wi-Fi router all have in common? I mean, at first glance, they couldn't be more different, right? But believe it or not, they share this fundamental, incredibly powerful secret.
And the answer is, they all run on the exact same kind of invisible energy. It's this force that's, well, pretty much everywhere in our world and all across the entire universe.
So, what do we call this mysterious energy? It's known as electromagnetic radiation, or, as you'll probably hear it, EMR for short. And let me tell you, getting a handle on this is the absolute key to understanding how so much of our modern technology, and really the universe itself, actually works.
So here's the core definition. EMR is energy that moves through space, not like a tiny particle, but as a wave. And this wave is made of two parts that are completely interconnected, an electric field and a magnetic field. You can almost picture them dancing together as they travel.
And the structure of this wave is actually beautiful in its simplicity. Just imagine an electric field that's oscillating, kind of wiggling up and down. Now picture a magnetic field wiggling side to side at a perfect right angle to it. And then the whole thing is moving forward, also at a right angle to both of those fields. So everything is mutually perpendicular, creating this perfect, self-propagating pulse of energy.
Now this is the mind-bending part. Unlike sound, which needs air or water to travel, EMR needs nothing. Its electric and magnetic fields just create each other as they go, which allows it to travel through the complete emptiness of space. This is precisely how sunlight reaches us all the way here on Earth.
So, now that we know what these waves are, let's talk about what makes them different from each other. Turns out, every single one of these waves, from a radio signal to an X-ray, can be described by two really simple properties: its wavelength and its frequency.
First up is wavelength. You'll often see it represented by the Greek letter lambda. The easiest way to think of it is just as the physical size of the wave. If you could just freeze time and measure the distance from the peak of one wave to the peak of the very next one, that distance is the wavelength.
And next up is frequency, which uses the symbol nu. This is all about how often the wave goes by. If you stood in one spot and just counted how many of those wave crests passed you in a single second, that count is the frequency, and we measure it in hertz.
Okay, so why do these two properties matter so much? Because the relationship between them is like a secret code that determines the most important thing about a wave: how much energy it carries.
And this illustrates the fundamental trade-off perfectly. It's an inverse relationship, kind of like a seesaw. If a wave has a very long, stretched-out wavelength, it's going to have a low frequency, and that means it has low energy. But if you squeeze that wavelength down, making it super short, the frequency just skyrockets, and it carries much, much more energy.
So the crucial point boils down to this simple but really powerful equation. C equals lambda times nu. It tells us that for any electromagnetic wave, its wavelength multiplied by its frequency always equals the speed of light, which is a constant. So if one goes up, the other has to go down to keep the balance.
Okay, so now that we're armed with that knowledge, let's take a quick tour through the entire family of EMR, what we call the electromagnetic spectrum. We'll arrange it from the lowest energy waves all the way up to the absolute highest. We'll start with the gentle giants of the spectrum, radio waves. They have the longest wavelengths and the lowest energy, which makes them absolutely perfect for carrying information over huge distances, for things like your car radio, TV signals, and other wireless communications.
Moving up in energy, we get to microwaves. Their shorter wavelength is great for communication and radar systems, and, as you definitely know, they're also exceptionally good at heating food. That's because their frequency is perfectly tuned to make water molecules vibrate like crazy, which generates heat from the inside out.
Next is infrared. You can't see it, but you can feel it as heat. Every object that has a temperature above absolute zero is emitting infrared radiation, which is exactly how thermal and night vision cameras are able to see in complete darkness.
Now we arrive at a very, very narrow sliver of the whole spectrum: visible light. This is the only part our eyes have evolved to detect. It gives us every color we see, from the lower energy reds all the way up the rainbow to the higher energy violets.
Just past violet on the spectrum is ultraviolet, or UV light. It's energetic enough to cause a sunburn, but it's not all bad. We can harness its power to sterilize equipment, and our own bodies actually use it to produce essential vitamin D.
Ramping up the energy even more, we get to X-rays. These waves are so energetic they can pass right through soft tissue like skin and muscle, but are stopped by denser materials like bone. And that gives us the incredible ability to see inside the human body.
And finally, at the very top of the spectrum, we have gamma rays. These are the most energetic waves of all, born from things like nuclear reactions. They are incredibly powerful, and in medicine, they can be precisely targeted to destroy cancer cells.
So, we've seen the whole family, from radio waves all the way to gamma rays. But why does understanding all this really matter? Well, because it allows us to see our world in ways that would be totally impossible with just our eyes.
Let's take remote sensing as a perfect example. A satellite doesn't just take pictures. It's an incredible detector that measures the specific wavelengths of energy reflecting off the Earth's surface. Healthy plants, for example, reflect infrared light very differently than sick ones do. This unique pattern of reflected energy is called a spectral signature, and by analyzing these signatures from space, we can map everything from forest health to where to find minerals.
And that's really the big takeaway here. Electromagnetic radiation isn't just some abstract concept from a physics class. It is the foundation of sunlight, your Wi-Fi, your cell phone, and medical X-rays. It's how we forecast the weather, study distant galaxies, and monitor natural disasters. It is fundamentally woven into the very fabric of our lives.
You know, in the end, maybe the best way to think about it is this. EMR is the language the universe uses to tell its stories. Each wavelength, from the longest radio wave to the shortest gamma ray, tells a different part of that story. And our technology? It's simply the tool we finally built to start learning how to listen.